Python is a standard for all industries, regardless if your background is web development or if your end goal is some new technologies like AI. Python will be intrinsic in all of those new technologies. The requirements for this course: you should have knowledge on the basics of Python, how to import libraries, how to create variables, how to define functions, concepts about OOP, and just the basics. I will show you in the first chapters architectures of RAM and the logic behind containers and why sometimes you want to use different ones. Some of the projects we will cover will be playing around with the Houdini API so we can control nodes, parameters, and automate some networks. We will create an HDA, we will deploy that HDA with Git, we will check some important concepts about Git, how to work with a pipeline, implementation, and the logic behind the steps of our production. We will check efficiency in searching algorithms. We will check how to traverse through graphs, how to create graphs and implement them as well. Some sorting algorithms, extremely important for our production. All the concepts of CI/CD, system design, encapsulation, security, how to deal with real-life datasets. We will implement the logic for a home pipeline so it can be scalable for a big studio. We will check concurrency in programming in a geometry context. We will create some Houdini projects. We will have an asset project, ingestion into the pipeline, going through Unreal Engine, checking some really cool stuff along the way. We will check the Python USD API for Houdini, which is DCC agnostic, it's not just for Houdini, but with the main logic, how it will communicate with other DCCs. By the end, we will have our first steps more into data, checking Pandas library, how to visualize and plot some 3D data, and how we interact with different libraries, creating Python environments and communicating that with Houdini or any other workflow you need. So if you want to jump in the boat of the technical side of things while maintaining your creative side of things, this is the best approach for you. If you're coming from a pure web development background, for example, you will be dealing with lots of 3D based technologies. So this is a great step for you to be familiar with 3D pipelines. What's happening behind the scenes in a production sense. I will show you how to write clean code and how we check code in a production environment, how to deploy this code, how to maintain this code. And we're going to use Houdini as our center DCC, as our main core DCC. The reason for that is there are many DCCs out there like Maya, Blender, Modo, and so many more. And I think Houdini has the best Python API. Most other DCCs will rely either in graphical interfaces or in the backend. There are some amazing tools, for example, in Blender or Maya, but those tools mainly involve a human clicking things and selecting things, so it's not very automated. They really split the way in graphical interface-based tools and in backend interface-based tools. Houdini is like this hybrid API, where you can even click buttons, drag windows, and do whatever you want with Python, either in the front end or in the back end. So it's a really essential DCC, and you're going to be surrounding this course based on Houdini. It's not just a Houdini tutorial-centric Python API course. It covers many things about software development, working as a team, what skills you need in order to progress in your career. We'll start with data structure and algorithms, big O notation, concepts about containers, hash tables, how to work with JSON files, really essential theory and implementations of graphs, search algorithms. We will check the Python API for Houdini. We will check how to create environment variables for a production. This can be in many DCCs like Unreal Engine, Maya. It's a production itself, how to deal with the backend of a pipeline. We will implement a really small home pipeline. If you're a freelancer, this will be really useful, how to communicate with clients. If these are your first steps in an industry, how to automate your process, how to get your first steps into this whole side of technology. So welcome, I hope you're excited. We will check so many cool projects and I will guide you through all of these steps. Hello everyone and welcome to the Python course for production. In this first week, week 1, you're gonna check all the basics of computer architectures and data structures. We're gonna start with one of the more important concepts about algorithms, and that's big O notation. It will take too long to explain and go deep into all about big O. So in the first videos, I'm pointing you to these 2 websites. They are excellent articles and you can check them in depth. One is from Free Code Camp and the other one is from Geeks for Geeks. You just have to literally just Google big O notation. There's gonna be lots of results, but Free Code Camp and Geeks for Geeks will point you to these two articles. Lots in-depth explanations, and we're gonna start with the basics for this, just taking in mind about BigO, and then we're gonna move into more of the computer architecture side of things. We're gonna check the basics about containers and how they work in RAM. We're gonna check about dynamic arrays, different kind of data structures, and how they interact with our system's memory. Those data structures will be basic arrays, dynamic arrays, linked lists, why sometimes you're gonna use a linked list instead of using a basic container like a dynamic array. So lots of theory and implementation for linked lists. We're gonna check data structures like JSON files. We're gonna check this API called JSON placeholder, which is a dummy API, but it's an excellent exercise to know how to work with the requests Python library. So we're gonna check this kind of posts and work with this JSON data. All about hash tables. We're gonna check about graphs as well, to implement graphs, theory about graphs, how they work in the backend, and the two main algorithms for traversals, which is depth first search and breadth first search. In the same level of graphs, we're gonna check about binary trees and binary search trees, and we're gonna implement a binary tree and a binary search tree. Taking these concepts, these first concepts in mind, which are really important, we're gonna dive into Houdini, because Houdini is also a user graphical interface based on graph traversals, which are the nodes, not just the node itself of the program. Anything can be transformed into a graph, and usually in a production, we do that all the time. If you think, for example, about the city map, or any kind of data you can transform into a graph, like a character rig, or the layout of a city, of an environment, or your level, anything, we're always transforming into graphs and creating lists so you can do a graph traversal like algorithm. So we're gonna check that by checking Houdini, and we're gonna do a refresher on the Python API for Houdini, how to create nodes, all the different places where you can type Python code, and get familiar with the Houdini Python API overall. Hello everyone, and welcome to the Python course for production. My name is Felipe. I'm a technical lead and full stack developer in the tech industry. I've been working in tech for quite some years now, in lots of different companies and roles, such as self-driving cars, small finances and big startups, game development, metaverse solutions, and some movies. Through my career, I've been in all sorts of roles and covering pretty much all sides of the spectrum, from hands-on developer, front-end, back-end, to project management, people management, and even driving the management of technologies for entire companies. I've seen some common things, especially in the entertainment industry, such as advertising, VFX, or game development. Sometimes the line between the technical side and the creative side gets really blurry, which is a really good thing. And people start jumping more in the boat of the technical side of things, not just for automation, but in general to understand how to do their job properly. And as a common thing, especially in newcoming artists, for example, I'm not saying they're doing a bad job. Quite the opposite. I've seen some amazing tools created by junior artists all the way up to supervisors. But not everyone has the background and knowledge in computer science, algorithms, and how a computer works in the background. So the purpose of this first chapter is to level everyone up roughly into the same line so we can go into the more advanced topics. So how many times have you tried to load, for example, a shot or an asset or a level, and then pass around files from artists and different kind of things like that? Or I just hit publish and it takes forever to publish, it takes forever to load the shot, the asset, or the level, and things become really slow. Most of the time is because the algorithms are not properly implemented, and stuff like BigO notation or proper use of data structures, containers and whatnot are not being properly implemented. So that's why we're going to jump into that first, quickly get that out of the way, and start developing. The main first concept will be BigO notation. If you Google BigO notation, you will get lots of articles. I will recommend this one from Free Code Camp. It's really good. And this one from Geeks for Geeks. Basically, if you have no idea about BigO notation, we're not going to cover all of it. It's like a big topic. But the essentials are key for you to understand. The way we measure algorithms is by something called the complexity analysis. And we will split that in two parts, time and space. And you will see this, for example, in chapter 5, time and space complexity. Time is not the time based on, for example, seconds or minutes or any of that. It's actually how many times is your algorithm running based on your input. As your input grows, how is your computation behaving? How many times is the algorithm running? And space is how much space is going to occupy in memory. Extremely essential, and you can't even start dropping Houdini nodes or doing some different algorithms in Maya or whatever, or the DCC or any kind of development if you don't have the concept in mind and if you don't do it properly. So to give you one example, if you have a basic container like this array, we're going to measure it in big O. So if you're doing, for example, an algorithm where you're iterating through every element in the array, and let's say you're just printing every single element inside the array, that's obviously based on your input, the size of the array. So for example, in this case, it's of size 5. Let's close the array here. So the algorithm will go 5 times, each time for each element inside the array. That will be O of n. N is the size of the array. So if n is equal to 5, and the algorithm is going one by one, that will be big O of n. If you're doing another algorithm where you're not going to iterate through each element, and the algorithm is not going to grow based on how much elements you're actually expanding in the array, for example, you're just printing the first element, that will be O of 1, also known as constant. This kind of measures is extremely essential to be able to develop something efficiently. And space, for example, let's say we're taking this array as an input, and you're doing a program where you're going to iterate through each element and, for example, multiply it by the power of 2. But you're going to output that as a new array. So your new array is going to be the same size, and then you will have your new outputs for each element. There will be n as well. So space in this case will also be big O of n. If you're going, for example, you're not returning a new array, for example, you're just printing every element in the array, keep in mind you're not using extra memory. You're not allocating new containers or anything like that. So you're not using any extra space. Therefore, space for that algorithm will be O of 1. Again, it's going to grow depending on your input. How is the computation behaving based on your input? If you have 10 million elements and you're doing an algorithm that's going to go one by one into the 10 million, will be O of n, and the length of the array. These are some of the algorithms you can implement. There are many more, and you're probably combining lots of them. As an example, logarithmic algorithm, big O log of n, is when you're using binary search, for example. We will implement binary search a bit later. Linear algorithm, the one I show you where you're traversing every single element on the array, will be O of n, the size of the array. If you're doing something else like superlinear algorithm, will be O, n log n, and things like that, when you're sorting arrays and different kind of things, and there are many more. The main topic and the main thing to get in mind is how is your performance and what you're doing with your computation. You will see this kind of graphs here. The chart, it will show you by colors efficiency in the algorithm. O of 1 constant is always the best case you can have. O log of n is really good. O of n is fair. It's going to grow exponentially as your number of inputs grows. O n log of n is bad, and these are the worst ones up here. So in production, we try to stay in this area down here, the orange to the green areas. So from O n log n to O to the constant, or O of 1. But it's not unusual to be in this area as well. For example, the case of matrix multiplication, which is intrinsic to data science, machine learning, and game development. So it's not unusual to be in this area as well. But we try to not go to horrible exponentials. So O(n) to the constant will be good if you know how to handle that. But if you're going into this horrible, as it says here, algorithms, sometimes maybe O and cube or things like that. This will never fly in production. Unless it's absolutely necessary to have those, it will never be there in an actual production. And we will try to improve those algorithms, at least if possible, to make it O n square or even better. So you think it that way. I've seen in production some Houdini scripts, for example. You just start dropping nodes, doing a for loop, and then they have nested for loops. After that, they have another loops doing things. You can probably save all that computation and make it all run in one loop, and things like that. You can't just drop loops and nested loops just for the sake of start doing things that way. You need to be aware of the computation. So let me give you one example why you need to care about that. The usual example is, let's pretend there's no internet and you need to find a word in the dictionary. I'm not talking about the data structure, an actual physical book, a dictionary, words and the meaning. If you need to know the meaning of a word, if the word starts with the character P, for example, you're not going to go to the first page starting with A, checking every single word, turning the pages until you reach to P. It's not how it works in real life, and that's how your algorithm is working if you don't do it efficiently. You're probably going to skip maybe to the middle of the book and see if you're like behind P or you're after P and things like that. Another example, if you need to grab, for example, vegetables from the supermarket, you're not going to go through every single aisle and check every single product until you reach the vegetable section. You probably go straight up looking at signs and things like that. That's exactly the mindset you need to have when you're doing algorithms. You can't just traverse everything at once all the time for efficiency. So if you're doing a program, for example, here where you need to fetch and calculate the middle element in the array, you're not going to traverse the array one by one. This can be millions in there. You just take the length of the array, divide it by 2, and you can immediately select the element you want. That will be constant time because you can immediately access the element you're looking for. So be aware of big O of n, check those articles, and always keep in mind the computation based on your input, what's happening, how many times is the algorithm running, how is your efficiency as you're developing. Hello. So before we jump in, I'll just briefly explain my workflow and the tools I use. Now, I'm a senior developer working in full stack. I've been working on this for years, and I don't use an IDE. In most programming workshops of courses, of classes, or whatever, I see lots of people using IDEs. It's not necessarily a bad thing. For me, it's just horrible to use one because it actually slows me down so much in production. And I'm a terminal guy. I live in the terminal all day long. Every single thing I do is probably most of the time in the terminal, even like sending mails, and I also have ChatGPT integrated in there. Basically everything I do, I live around the terminal. If I need to connect to external servers or other computers around the house, I'll just do it from one machine. And I work that way. I learned to use Vim probably like 6 to 7 years ago, and switching from that to a regular text editor, such as an IDE, for me is absolutely terrible. I feel like my hands are tied behind my back and I try to develop somehow like that. And the more you use it, the more you know what I mean. I'm not necessarily telling you need to use this, but a teacher once told me, are you digging your tunnel with a spoon or with a bulldozer? That's the comparison. For me, NeoVim or Vim is one of the greatest tools for efficiency. Now, Vim is the old architecture, but NeoVim is a whole community. And we're talking about hundreds of plugins, so many development for this. There's entire companies dedicated just to NeoVim development, with Lua plugins and all sorts of new workflows and tools for NeoVim. There are many developers that only use NeoVim, and the majority of people I know at least uses a Vim-like emulator. So the main tool I use, my main editor, is NeoVim. If you just Google NeoVim, you can go here. If you hit install, it's going to take you to a repo. There's a bunch of binaries and stuff like that. You can also build it from source if you want, or use some kind of package management to install it. Regardless of that, you will have that in your terminal. The other tool I use is Tmux. Tmux is also essential for me. I can't imagine live without this, especially being a terminal guy. So I'll show you this also really quickly. And NeoVim itself is just a program in your terminal. So you need to customize it so it works as you intended to work with your own shortcuts and stuff like that. I've been using my configuration for lots of years now, but lately I switched to use the Primagen's configuration. Primagen, this guy, I'm pretty sure you know him. If you search for this video on YouTube, 0 to LSP NeoVim RC from scratch, he will guide you how to configure nvim. And honestly, I just give it a try, and this configuration is so good that I can't stop using it. And it's basically a repo, and he will show you how to configure everything. There's so many things in the world of configuring and playing around with Vim or NeoVim. We're not gonna go there. I will just show you why I use it. So if I jump in my terminal, if you type nvim after you install it, this is it. This is your editor. It might look really different than the default because, again, I have the primes configuration, and for me it's absolutely essential. So why you want to use it in the first place? Let me show you with some examples. So I'm here in some random file. If I do neovim, for example, this YouTube metrics script I have here, this is a regular Python file in Vim or neovim. There's gonna be some shortcuts. There's a learning curve to use Vim. I'm not gonna lie, it can be really steep, but it will depend on you. First of all, it's all about efficiency and productivity. I'm gonna do things slow, but this is not how I work in production, but for sake of demonstration, I'm gonna do things slow and grabbing the mouse with my hand and pointing things. I'm not gonna show you like my shortcuts or stuff like that. I just want to think about functionality. So if I wanna go to the end of the script, I can just go immediately to the end of the script. I wanna go back to the beginning, then I'm there. You see? Let's say I'm trying to aim for this class definition here. I can immediately jump there. Let's say I'm trying to go down in pages. I can do it like this. You can see the middle of the screen, the cursor stays there, and I can just jump by half and quickly navigate through my code. Let's say I want to have everything inside these parentheses right here. I want to select that, but maybe I'm up here or something. How can I quickly jump that? I'll do it slowly, but this is not how I work again, but I'll just do it slowly so you can see. So everything down here, all of this, I want to select that immediately, even when I'm up here. The way I'm gonna do that is with some shortcuts like this. Boom. Now I'm selected everything inside there really, really fast. At some point, when you get familiar with your shortcuts, you don't even think about that, right? So for example, if I go down here, let me go up until this level. I can select the whole line. I can keep growing my selection. If I want to, I can go down to that print statement below really quickly like that. Select everything in between parentheses. Done. I can delete that. I can keep adding new words, stuff like that. I can undo that. If I want to go, for example, to this videos word here, let's say my cursor is currently there, but I need to replace that file. Instead of videos.pkl, I need something else. I can immediately do that and start doing something else. Even when I'm at the middle of the word, I can do that. If you don't do that, for example, let's say I'm here, you can see how I'm jumping to the beginning and end of the word. I can also skip it like this, jumping between these backslashes or forward slashes, whatever they are. It's so efficient the way you work with NeoVim that you don't even think at some point. You just fly around. You can navigate really quickly, vertically and horizontally. So if I want to go to the end of the line, I can do that immediately. Now my cursor is there. Go back to the beginning. Let's say I'm at the end of the line again. Let's say I really quickly want to jump into this equal sign or this key. I can do it like this, and now I'm exactly in that word. You see, there's so many shortcuts. There's so many conveniences you can use with Vim. It will take like weeks to name everything you can do it in here. But it's so efficient the way I work with this, the way everyone works with NeoVim, that you don't even have to think about IDEs. I don't think you can do this kind of things in an IDE unless you install an NeoVim emulator. But I don't need all the fancy pop-ups from an IDE, all the different things that just making things slower, because all the functionality I have is here, right? Now you might be thinking, what about like different files? Because I have one window right now looking at this file. I have some tools for that. Here you can see all the files in my current folder. You can quickly jump into that. If you see on the left side, I also have this configured to relative line numbers, you see some weird stuff. Maybe you don't know what's happening here. Trust me, once you switch to relative line numbers, your world changes completely because you move so fast that it's almost ridiculous. Why relative line numbers? This line is the current line I'm in the whole program, which is line 51. Let's say I want to jump really quickly into this line. That will be 12 up, which I can do that by typing this. Now I'm immediately in that line, which is line 39. If I want to jump into this line, name equals main, that will be 15 down. And I can jump immediately into that line. If I want to go to the beginning of the line, to the end, whatever I want to do. It's so fast the way you navigate through Vim. It's really, really, really efficient. One really cool thing we also have is, for example, let's say this insert function. This file can be really, really long, and at some place in the file you're defining this function. I can quickly jump by doing that. You see? I immediately jump where the function is being defined. There's also so many other things. For example, there's going to be a lot of this definition file with keywords in the script. Let's say I want to replace all of those globally in the entire document. I can do that with Vim shortcuts as well. If I do def, you can see it's marking all of those. I replace it with something else for everything. And now you see everything. Obviously, it's going to fail because you're not supposed to do that. But I just changed for that. So you can trigger all the instances of words. You can change stuff just in one line. There's endless possibilities, really, with Vim. It will take weeks or months to explain everything, but just try to play around with that, and it's going to change the way you develop and you work in general. Another really important tool is an LSP, which is a language server protocol, which I do have installed and configured with my nvim as well. This is really great, and you can install as many as you want depending on your programming language. So obviously I have one for Python. And if I start doing something incorrect, like setting a variable like this, it's going to give me an error in there because this is being fetched from a server, checking that the language is correctly implemented or not. You don't have to compile this and then check if there's some error in your code. As you're typing your code, it will tell you if you're doing something wrong. It's not just for that. It will guide you in auto-completion, in how to structure things, and how to make things even faster than using just regular nvim. Again, this kind of thing is really, really useful. The one I have, you will see that in the video as well for the explanation, but it's called LSP0. And there are many language server protocols, and there are many, many language servers, which you can install and implement your own if you want. Now let's talk about tmux. Tmux is a terminal multiplexer. What that basically means is you can have multiple sessions in your terminal. Extremely key for development. So if I run a session here by just typing tmux after you install it, something is happening down here if you see. This is my first window in the session. You can have nested sessions, and it's really crazy once you start playing around with this. I'm just in one location in my directory, and I happen to have some files here. For example, if I start editing this same file, I'm doing all that development here, but I can open a new window, and then I can, for example, edit another file here. Can be really large files. You're doing some things here. I'm working in this directory, and I can immediately jump into the previous one. I create a new session, and maybe I'm monitoring a server here, or I'm doing something else like answering mails or whatnot. Maybe I'm into another location. I can quickly jump back to the first one. If you see down here, the star will tell you in which window are you currently into. So, and you can also change, for example, the names. This can be my main file. I'm editing my main file. I can jump to the first one. I can change the name to this. This can be my class implementation or something like that. You can give names. You can keep adding new windows. Maybe I'm doing something else here, and let's give it a name. And this is monitoring my server, for example. So you can quickly jump back, like, okay, I'm doing my development here in my class. Maybe I need to monitor my server to check what's happening here. And then maybe I jump into my main function. You see how it works? If you close this and you reopen it, the session is still active and you can have nested sessions. Really, really handy. You can immediately jump to different files. You can copy in between them. You can make that intercommunication. Jump that, monitor your things, your utilities. This is working, great. And that's why you use tmux. Tmux is really, really essential. Again, I don't want to have that mental charge of an IDE and checking like a million tabs and there's like a million folders. At the beginning of my development, I will restructure these windows. And then without thinking later, I just jump in between them. Okay, I know this is where I'm doing my main development. This is where I'm creating my class. This other window is to communicate with different things and stuff like that. So using a mix of tmux and nvim, my productivity is sky high. It's really no comparison. The only reason I use IDEs is when I'm reading someone else's code. When I'm checking PRs, in my position at my job, I need to check a bunch of code, a bunch of implementations of different researchers and stuff like that. Honestly, even for that, I still use nvim because I can quickly jump around between definitions and different files and header files and stuff like that. But sometimes it's easier to just lay out that in an IDE. It's up to you. Most of the time, I will say in my career, in my day-to-day job, I will stay like 90% just in nvim and do everything in there. But it's up to you. Hello everyone. Let's just do a couple of more overviews about big O notation. Basically the main idea is whenever you're doing an algorithm and you have some input elements and output elements, just need to be aware on the computation and how is your algorithm running in terms of time and space. So for just basic practices, every time you have, for example, a for loop. So you have some container, let's just stick with basic array, and you need to do some operations in here. Now, by running each element, you know this is O of n being the size of the container, of all the elements inside the container. Now, if you have other operations, if this for loop ends, and then you have another for loop, for some reason in your program, maybe this is not running in the container, it's just running some iterations, maybe like 10 times. All of this will be a constant. So it doesn't count because the majority of the operations are being taken by this first loop. So time in this specific case will also be O of n. Now keep in mind, this is just one input, one array. But let's say we don't know the size of this array and maybe we have another input, which is a fixed size array. And this can be, for example, the number of fixed characters or something else that you know is going to be of a fixed size. Practically speaking, maybe this new array as an input could be bigger than this one here, but we don't know that. And the main concept in Big O is always take the worst case scenario. So worst case scenario, this first array, let's call this array A and this array B, it can be millions of elements and we know this is a fixed size, therefore this is a constant. Second rule, we always drop the constant. So for example, let's say this array, array A, was of size 100 elements. And array B is of size 4. Since we don't know this, like practically speaking, this could be size 100, 2 million, we don't know. But array A will take precedence over array B, because this is a constant, so we're always going to drop this, and the time complexity of this algorithm will still be O of n. Let's do something on the side here. For example, we have a for loop running through all the elements in the array, and then we have another loop inside the main loop. You know that for each iteration, all of this will perform. Therefore, the time running for this will be O(n) squared. So it's not always n as the main element when you're talking about big O. It can be something else. Like for example, let's say again we have, let's do some space here. Again, we have two inputs. We have array A, and then we have array B. But in this case, we don't know the size of either of these. It can be millions of data inside each one of these. We don't know. But the algorithm is going to iterate through each one of these, right? So if we have a for loop, maybe this is running for array A first, so this one here. And then this will end, and then it's going to take the second array, doing another for loop, and it's going to finish and maybe do something else in our program. We need to traverse each one of these, but we have two inputs. This time we can't just say it's going to be O of n. Ideally, you will say, since we have two inputs and we don't know the size of each, but we know we're going to iterate through each of them, running complexity on this will be O of AB. We have different elements. We're establishing n if you only have one container, or not just a container, if it's looping or running n amount of times. N is the standard for big O. Now, in the case of trees, it's going to be different. If you have a tree data structure and your algorithm is going to fetch all the nodes, that will be O of n, because you know you're going to iterate and graph all the nodes. So you need to iterate through each one of the nodes and graph the data, for example. But if this is the case of a binary search tree, for example, we will see about these kind of data structures later. We do have some conditions where, for example, depending on the algorithm, we will never visit this branch or this whole branch. And then we keep doing different kind of isolations of the whole data, of the whole data structure. Therefore, we can assume the algorithm for this, in the case of a binary search tree, we can be log of n. And different ways of measuring different algorithms. I saw it in a book once, and this is a really good example. Let's say you need to paint a fence. You need to do a program to paint a fence in your house, in your garden, or whatever. If you keep in mind of the elements on the processes to get this job done, the fence will have width and height. You can't just paint the fence and the width. It will be like going horizontally forever. Therefore, the algorithm for this will be big O of width and height, right? But what happens if you have another element that is going to involve and is going to alter this algorithm? For example, let's say we need to use some number of paint layers for this specific task. We don't know how many, but still going to be affecting our running time for the algorithm. So if we establish, for example, L to be the number of paint layers, this algorithm will be all of these, big O of width, height, and the number of paint layers. So that's the main concept you need to grasp when you're dealing with these kind of scenarios. Sometimes it's misleading if you have one container, for example, and you're doing a for loop. Let's do it down here. You're doing the for loop in the container, and then the loop ends, and then you're doing another loop. This is not O(n) squared, even when you have two loops and you see two loops here, because it's not growing exponentially depending on the size of your container. If you keep adding more elements, you're still doing just two loops, and they are running, even when you see it separately, they are running n amount of times as the size of the container. So the running time for this, practically speaking, will be 2n, right? Because for n, for the number of items in the array, you're running it 2 times. But again, one of the main rules, we always drop constants. So running time for this is still big O of n. So try to check those articles, try to get familiar with this, and it's going to be vital for you along the way. Let's take a look at the architecture of a program. What's happening when you're typing your code and executing that? So these are the steps the computer will take. You're typing an English-like syntax. You're typing words, characters, numbers, floats, instructions, and all of that. The computer won't understand any of that. the computer speaks in binary, in machine language. So whatever you type in, the computer has no idea what you mean. So we need some steps to be able to transform our code into machine language. If we're starting with the source code, this is what you're typing in your editor, in your programming language, all the words, characters, instructions, and whatnot. When you execute that, the second step will be to go into a compiler. A compiler is another program. The compiler will tokenize all those characters, all those words, and everything you have in your source code, and will convert that into assembly. Assembly is another programming language. This was designed so humans can write something closer to machine code. But the machines still don't understand any in assembly. The next step will be an assembly needs an assembler, so it can transform that code into machine code. But it's not ready yet. The next step will be an object file. This file carries machine code, so it's almost there for the machine to understand all the instructions. You will see a bunch of these when you're executing, for example, your program in Visual Studio with C++. We are checking all this architecture in a program like C++, for example. After you have the object file carrying machine code, it's almost there to be an executable file. But you need one more step. In your program, you can be calling many different libraries for the programming language. You maybe have different header files and lots of different modules. You're combining those and calling them into your main application. But also you're interacting with your OS. So for example, if you're doing a graphical interface in Linux, for example, you probably need to speak with the X11 API. So for all of that, you need the linker. The linker will link all the header files, modules, and the libraries from your OS to your main application. Even if you're not calling any external library or interacting with the OS libraries, you still need the linker, otherwise it's not going to work. The linker will link all of that, and now here finally we have an executable file. So if you're doing a simple program, like for example just printing hello, all the instructions you'll be typing in your source code, it will go through a compiler. The compiler will transform that into assembly. An assembly needs an assembler to be able to transform all that into machine code. And now the object file carries that machine code. You need a linker to link the header files, modules, and libraries from your OS. And then finally here in the executable is going to print hello. As you can see, there's a lot of steps, so many things happening. That's why efficiency is key. Now this is in something like C or C++, which is still high level, but is a little bit closer to machine code. In programs like Python, there are so many things happening in between. It needs a translator, it has to be compiled in maybe using C, Python, and many different things. Python has so many things happening behind the scenes, that's why it's so dynamic, but that's why it's also considered so slow. It has to be transformed into bytecode, it has to be transformed into many different things. And then you go into the steps of doing compiler, assembly, and all the stuff. So be aware on how you're implementing your program, all the steps happening behind the scenes, and that's why we need to care about efficiency. You need to understand how a computer works and how it's operating in the background. We're going to start this workshop with containers. This is the most basic container. An array in Python is called a list. And the way it works is an array is a contiguous data stored in memory. So if we abstract away the fact that this is an array of integers, what's happening behind the scenes in your computer, all of these will be allocated in RAM. RAM is conformed by memory addresses, so you have an address of every actual element in the array. If we start deconstructing this, let's take the first element in this container. 1 is an integer. In your computer architecture, you're probably using a 64-bit architecture. Regardless of that, it's going to depend on the compiler and the OS, but usually and as a standard, an integer is going to occupy 4 bytes of memory, which is equal to 32 bits. And the underlying architecture, if we deconstruct this, for example, just this element in the array, the first element, which is 1. In memory, you have a bunch of transistors, basically a bunch of zeros and ones on and off. That's why we work with the binary system. 1 in binary is going to be 1, padded with 7 zeros. I'm not going to do all of them, but you get the idea. This will be a location in RAM. So this element, regardless if this is a 64-bit architecture, it's just going to use 32 bits. Each one of these is a bit, if we split it like this. Now the box itself will contain 8 bits. So we need 3 more to make it 4 bytes or 32 bits. If this is 1, it's going to start in binary 1. It's going to be padded with 7 zeros, and each one of these other boxes will contain 8 zeros, each one for each bit. I'm not doing 8, but you get the point. They are filled with zeros. So that's an integer. The reason it's stored like this is called the endianness of the RAM. We're not going to go there. So for the rest of this explanation on containers and arrays, we're just going to abstract all of these away. And we're just going to use one box in a grid. But keep in mind this is happening. Now, if you're creating something called a long integer, you're actually going to use all 64 bits of your machine. So the remainder 4 on this side. If you're using pointers, a pointer itself in the system will also be 64 bits. As you can imagine, there are lots of things happening just with one element in the array. I'm going to keep repeating the same, but efficiency is key when you're dealing with data. So I have this quick grid here to explain how it's happening in RAM. All the stuff in here, all these 32 bits, we're just going to abstract it away, and let's pretend all of that is just one of these cells. So in RAM, in this container, the address of the first element will be this one. Of the second element, this one, and so on. That's why an array is a data structure that is contiguous in memory. So in Python, an array by default is a dynamic array. That means you can expand it and you can shrink it as you like. You can keep adding more elements or remove them. You can make it grow or shrink. In other programming languages, such as C and JavaScript, for example, it's more stable because you can define the size of the array and make it immutable. But in Python, it's not the case. In Python, you can also have different data types in the same array. So this one can be a string, and then an integer, then a float, then a dictionary, and so on. It's really convenient, and that's why Python is really easy to type and start manipulating it. But behind the scenes in the backend, there's a lot of things happening. So let's take a look at how dynamic arrays work. If I draw like a small version of this array, for example, it has 1, 2, and 4. So let's say we only have this array. By default, Python will actually allocate empty spaces in the array. I don't know how many, but you have a padding of empty spaces in memory locations, like in these ones here. That way you can keep adding elements. For example, you're adding 5, 7, 8, another 2. Maybe you want to add more. At some point, as you can see, you're running out of space. The way dynamic arrays work is, at this point, you have all of these in-memory addresses, all of these elements in the array. But once you run out of space, the system will actually copy the entire array into new memory locations. So it's going to wipe these addresses. It's going to copy all the previous elements, and now it's going to allocate new space for the new array. So if you fill up your original array, it's going to copy everything. And now, for example, the previous address of this element was here. Now it's going to copy all of that. And for example, it's going to allocate new ones here. So it's going to allocate for the new array. And at the end, it will allocate empty spaces as well for the padding. So if you make your array grow more and more and more, as you can see, you're copying the array every time. You're running out of space of the padding at the end, and it's going to copy the entire array into new memory locations. Can be really, really memory consuming and extremely inefficient at some point if you don't know how to manage it properly. So as you can see, sometimes it's a little bit risky to just blindly choose a dynamic array as your main data structure. So let's do an example here. This time I'll do it differently. I'm just going to allocate an array in some boxes. And let's have numbers 1, 2, 5, 7, 8, and 10. So we have a data structure, the same array is a list. And you know how it works in memory now. Maybe these are the shots in your VFX house, right? For some reason, you need to have it in order. And just for simplicity, we want to keep it as it is. Obviously, in production, a shot can be like this and some other data. We're just going to keep it as this is shot 1, 2, and so on. So maybe we're doing this shot because another house is doing shot 3 and 4 and stuff like that. And in your company, in your system, you need to have this in sorted order. And maybe, for example, let's say the client now says, okay, we're going to take shot 4 from the other vendor, from the other VFX house, and now you guys have to do shot 4. So now we need to introduce in our data structure, in our system, we need to allocate shot 4, which will be here in between 2 and 5. How are we going to proceed that, thinking in how all of this works in RAM? I'm going to probably repeat this a lot in this workshop, but always think in big, big numbers. We're thinking production here. For simplicity, I'm showing you tiny, small arrays, but this will be thousands of data entries, right? Could be, in this case, is the VFX shots we're talking about. Can be the polygons in your mesh. Can be all the polygons in all the instances and all the objects in your scene. In data science, can be these thousands, millions, even trillions of data entries. So it's going to be exactly the same concept every time I show you something like this. It doesn't matter if we have 2 elements, we're thinking in big scale production. So it's going to be like massive amounts of data entries. So how do we insert that in this array? What we need to do basically, for example, if I do like a new empty box here, what I need to do is shift every element to the right. So 10 now will go here, and then 8 is going to go here, and 7 go here, and so on and so forth. At the end, we will have a new empty space here, and then we can allocate 4 into our new array. But let's take a look for a second on what just happened here. Basically, this side of the array, we had to move every single element 1 position. So maybe in your data entries, you can have 20 million data entries here. So each one of those 20 million will have to move 1 to the right. As you can see now, this is extremely inefficient because inserting in an array is going to be big O of n. The worst case, we need to introduce this guy at the beginning of the array, and then we have to shift the entire array 1 position in order to allocate that. So how can we improve that? We're going to view another data structure called a linked list, especially a singly linked list. So a linked list is another data structure. So for example, let's say we have some similar numbers. We have shot 1, 2, 3, 5, 7, and 10, for example. Obviously, we can have, again, think about big scale, millions of data entries. The way linked lists work is by nodes. So each one of these will be an actual node. Forget about Houdini nodes, we're talking about something different here. This is a node class, so each one of these will be actually an object. So we're talking about shot, for example, VFX shots in this example. Obviously, your shot will have lots of data and metadata, right? Like length, number of sequences, vendor, IDs, and many other different things. For simplicity, we're just gonna take care, like in this example, the shot itself only has 1 information, and that's the shot number. But indeed, this is an object. And what conforms a linked list is actually the node itself with all the information, but we also have a pointer to the next node in the list. This pointer is a link. That's why it's called linked list. So this next node will have another pointer to the next one, and so on and so forth. So the way a linked list is conformed is you have a head or a root, and then you have all the elements in the list, and then you have a tail. We know it's a tail because, as you can see, it's not pointing to anything. So the next pointer of the tail is going to be null pointer, or in Python, it's going to be none. That's how we know this is a tail, and we know the head because it's the starting point and all the elements connected in here. So now let's keep track of the same example. Let's say now we're being granted SHOT4. How do we introduce that into our linked list? How do we insert this element into the linked list? And our purpose is to introduce it in order, so it will be in between 3 and 5. So we're going to create that node, and we're going to set, okay, we need to be able to reference the previous node we're trying to insert. In this case, the previous node will be 3. And we know the information about this node. We know what it contains. In this case, it's just the shot number, but we also have the next pointer, which is pointing to 5. We can say now, okay, I just created a new node in space. It's not connected to my list, but the next pointer is going to be the same one as the previous node. So now we can create this connection. And then we say the previous node now is going to point to this newly created node. As you can see, and now we forget about this arrow. As you can see, we're not shifting anything in the array in memory. We're not moving anything else. We're just moving these arrows, basically. So insertion in a linked list is going to be O of 1. It's constant time. So let's see how it works. Remember, in an array, each element was contiguous in memory, but it's not the case in a linked list. They're going to be randomly placed. So for example, the address of 1 can still be here, but maybe the address of 2 is somewhere down here, and the address of 3 is maybe somewhere over here. It's going to be randomly placed. But we have the pointers. We know that the next one of 1 is going to be this address here. So we have that communication. We have that pointer pointing here. And we have also this pointer from 2 to 3, which will point here. So if we're introducing a new node, for example, 4, somewhere in here, we just have to move these arrows as we like. Instead of pointing to one specific address, you're going to now to point to a different address, to the newly created address. That's why it's so efficient. We're not shifting anything. We're not, adding extra space or padding or anything like that. So let's talk about indexing and some of the problems we have with linked lists. Just to clarify this, inserting is going to be O of n if we have a reference to the previous node we're trying to insert. If we don't have a reference and we need to navigate and iterate through the list, it's going to be O of n. So let's talk about that a little bit more. For example, I have here a linked list, and then let's do an array with the same numbers. 2, 3, 4, 5, 7, and 10. This is the usual array, and the first one is a linked list. So the problem with linked lists, even when it's so efficient to insert, is actually indexing. If you want to index in an array, it's going to be constant time. That's O of 1. In the backend, it's happening some pointer arithmetics, but we don't care about that. But basically, it's O of 1. For example, if you're trying to grab index 1 from this array, it's going to output this number. So the output is going to be number 2. So if we call this S, and maybe call this L, if we say S of 1, it's going to give you this one, so it's going to print out, or whatever you're trying to fetch, the value is going to be 2. In Python, if we say, for example, S of -1, it's going to give you the last element in the array, so it's going to output 10. So if you do S of 2, it's going to output this guy. So it's constant. You can immediately access whatever index you want in the array. In a linked list, that doesn't happen because we don't have indices. Remember the way it's structured actually in memory. These are randomly placed in memory. They're not contiguous, so you cannot just index it. And that's one of the main issues with linked lists. For example, if you're trying to fetch this guy here, you need to traverse the entire list. You need to start at head, go one by one until you reach the node you're trying to fetch, and it's going to output the value for that. So this is what I want you to have in mind if you want to use one data structure or another one. So if you're doing an operation where you indeed have reference to the nodes, and your operations involve in inserting and deleting a lot, deleting a node from a linked list is, again, just moving those pointers, breaking the connection, and you're done. We're going to implement this with code, by the way, in a second. But maybe if you're doing just a data structure where you need to append just at the end and you don't care about this traversing, maybe you're better off with an array. Or if your system is going to be more important to index fast, then you can do this data structure instead of this one here. It's up to you as a developer, as a technical person, to actually know your data structures and to actually implement them well. Just as a quick overview, we are going to jump in and start developing these data structures and some tools in Houdini, but we need to see some very, very useful and common data structures first. So as a quick overview, the other data structure we will see is the dictionary or hash table, because we're going to be using lots of requests and JSON files. This is one of the most important data structures you can actually use in production. It's a key value pair data structure. As you can see, keys, for example, are A with the value of 5, B with the value of 2, C with the value of 12. The value itself can be a nested dictionary or can be an array or can be in different data types in Python. And the way it's working is actually they do have in the backend a linked list linking the key with the value. Really, really important data structure. We're going to use this one a lot. And the other one we're going to see is graph and trees. Graph, not only in the concept that Houdini is literally graphs in the nodes itself, but every single possible graph we can actually create in production. Even a rig can be a graph. If you think of a rig of a character, for example, it's a parent-child relationship, so it's going to be a graph connection, and you need to know how to traverse through graphs, and also with trees. So we're going to see those data structures as well as we advance through the workshop. But next, we're going to actually go hands-on into code and implement a linked list. So let's implement a linked list in code. We're going to stick with singly linked list. There's also another data structure called a doubly linked list. It's basically the same, but you also have reference to the previous node. So you have pointers pointing to the previous node. That way you can traverse forwards and backwards. But for now, we're just going to keep it simple and stick with a single linked list. So what we need to do first is create a class. I'm going to call it node. And we need to define a constructor. We're going to pass the constructor a new value. This will be the value of the node. And we also need the pointer for the next node. By default, it's going to be equal to none. And all we have to say is the value of this class is whatever value we're passing on. And the next pointer is whatever next pointer we're passing on to the class. And that's it. Really simple. Obviously, in production, it will contain many other things like, many other data and IDs and stuff like that. For now, it's just keeping it really simple. It only contains the value itself of the node and the pointer to the next node. Also, in production, we will implement a class to actually take care of creating this linked list. A class can actually push nodes into the list, delete nodes, append to tail, append a new head before all the lists and stuff like that. For now, we're going to keep it really, really simple. So let's start creating some of these nodes. We're going to create them in space in memory locations first, and then we'll do the links. So for example, let's say I'm going to have my head is going to be equals to an instance of that class, and we're going to pass in the value 1. Let's create a middle node, another instance of the class, let's give it the value 2, and let's create a tail. And let's assign the value 5, for example. Really simple list, just 3 elements in the list. I just created the nodes in space in memory allocations, but they're not linked yet. So let's work on the links. We can actually move those pointers and say, hey, head, your next node is going to be middle. We do middle, that next is going to be equals to tail. Tail is already none, but you can add them anyway, so we keep consistency. Sorry, I have a typo there. That's next. That way we have now our list, we have our nodes in memory allocations, and we have the links. So let's create a function to actually just print that list. Let's call it print list. And we want to pass in a reference to head, the root node, the beginning of the list. So the logic is, remember, you need to traverse all the lists from the beginning, in this case from head. So our condition is going to be while head is not none, which means while you not the tail, for example, just give me your value. You can say head.value. And now we need to tell head is now the next one. So we're traversing through the list. We need to call that function somewhere here. We're gonna print list and we're gonna pass in head. So let's execute this, make sure it's working. And there you go. We have the list, just 3 elements, 1, 2, and 5. Now, how can we insert a node? Let's say we want to insert a node in between 2 and 5. The same example, we're trying to insert node SHA-4 or node 4 in between. So let's do that. We're gonna create another function. Let's call this one insert at. And now we need to pass in the previous node we want to insert. In this case, will be 2. So let's do previous. And we need a new value for the node. So first of all, we need to allocate one of these nodes in space. We're gonna do that. For example, let's call it new node. It's gonna be another instance of that class. And we're gonna pass in whatever new value we're passing into this function. Now we need to point it, new node that next is equals to whatever was the previous next pointer. And now we need to say previous that next is equal to the new node. So let's check this one here. Let's do some printing here so we can actually identify that. Let's call this one original list. We're gonna print the original list and then we're gonna modify the list. So let's call the function insert at. You're gonna pass in the middle pointer. Remember, we do have a reference to this node here, the middle one. That's gonna be our previous. And then we're gonna pass in a value, SHA-4. And then we can just, for example, I'm just gonna copy this. And let's call this, I have a typo there, modified list. And this one is gonna be the original list. Okay, let's compile that. And then let's run that. And as you can see, now we officially inserted a node in between 2 and 5. And now we have SHA number 4 or node number 4 in here. You can see the original list and the modified list. We just inserted a new node. But be extra careful with that step. Let's take a look at what's happening here again. Take a look at the order. I'm moving those arrows. I'm moving those pointers. It's really, really important. Let me go back here. Let's remove those arrows. So we're just dealing with a singly linked list. So our purpose is to insert this node. Obviously, we don't have this 8, but just pretend it's the same list. Right, we're creating a new one in space. The order you set these pointers is really, really important. For example, let's say we have more nodes here. Right, we have a lot, like tens of thousands in our list. It's basically really, really important information in our company, in our system. If I create a new node, and first I set the pointer of previous to the new node, so this one goes here, take a look at what just happened now. We lost this connection here. Therefore, everything here now is gone forever. We just lost our entire system, our entire shots, and you just basically just brought down the entire production by doing that. You broke that link. So all of this doesn't exist anymore. If you break that link, all this remainder of the list is gone forever. So the proper order you need to do is create the node first, and then you set the node is to whatever was the previous one of next pointer. In this case, the new pointer will go here like that. Now it doesn't matter if you lose this connection because you're gonna move this arrow anyways, because now we're gonna move this arrow to this one. This one now has all that connection of the remainder of the list. And if you just move that pointer, we're not losing that connection, and now the new connection goes like this to the remainder of the list. Just keep in mind that really, really important on the order you actually establish those links. New node first, you create a new node, you set the pointer of that one first to whatever the previous pointer was, and then you set the previous pointer to that new node, and that's the order you want. Just one thing to keep in mind here. We are creating a new node by using this function, insert add, and inside the function is where we're actually allocating a new node in memory. We're storing that address in memory, and then we are creating that and linking it with the pointers to our linked list. But now, since the beginning of the list, the first 3 elements were actually hard-coded, like head, middle, and tail, we don't know which node is this one. Again, we can have thousands, millions of nodes in our linked list. So if you want to have a reference to this node, it's really simple. You can basically just return the node at the end. That way, since this function has a return value, you can actually store that in a variable when you're actually calling in the function. And you will have a reference to that node. Whatever name. Obviously, it will be a very descriptive name corresponding with the data you're parsing into the node itself. So let's start talking about dictionaries or hash tables. It's the same thing. Really powerful data structure. We're going to be using this one a lot, not just for API calls, but for many different things you will see later down the chain. Really powerful data structure, key value pairs, and indexing is going to be constant time. So let's do a quick variable here. Let me jump into my editor. So I'm going to have the variable d, and that's going to be of type hash table, and we're going to have some keys. For example, a, and the value is going to be like 50. And maybe we have b as a key, and the value is maybe a list. It can be like that. It can be anything. And then we can have something f, I don't know. And the value can be another string. And last but not least, let's have something else like c, and we have an integer as value. So you can't have 2 repeating keys. It doesn't work that way. This is basically unique keys. That's why it's so powerful, and you will see this the more you use it, why it's so powerful. But basically the keys they have to be unique. You can't just allocate a new key called C, for example. It's not going to work. It's just going to error this, and the data structure, it doesn't actually work. So the way you index that, for example, if we just print D, and then you pass in the key you want to index, let's go for F. This will output this string right here. So if we print that, now you get the value of that string, of that key. So we can actually iterate through the data structure. You will do that by iterating through key and value pairs. So for example, if we say for key value in D, that items, you need to specify you're actually looping through the items, because by default, if you don't specify that, it's just going to loop through the keys. And if you have 2 values, it's going to give you an error. You can't unpack 2 values in just one linear data structure. So by doing that, you can actually now print either the key or the value or both. We're going to print both. And now you can see that's our dictionary, keys and values. So one common format you'll be working with all the time is JSON files. In production, this is used a lot, and especially on websites when you're doing API calls, you're gonna see JSON files all the time. A JSON file basically means JavaScript object notation, but don't get confused by the name if you're not familiar with JSON. It's just a dictionary. So I'm using this website called JSON Placeholder so we can test some dummy data. It has some great examples. I just opened, for example, these posts. And the JSON file will look like this. Look how well organized and pretty that looks. So this is the ultimate structure you want for your dictionaries. You have the key, and the value is a nested dictionary. So it will have another keys and values, and you can have more like that. But the main idea of using JSON is to have this kind of structure. So if we come back, Python comes with this one predefined, is by default. So we're gonna import JSON, and let's create some new data. It's gonna be a dictionary. So let's have something, for example, key 1, and the value is going to be an integer. The keys can also be integers, it doesn't have to be a string. And maybe we have another key, and the value is a nested dictionary where we have key, value, maybe another one, key, value, and maybe we have another one outside, like that. Keep in mind, I'm doing this horizontally. I'm just adding a new dictionary just for testing purposes. So how can we write that dictionary in a JSON format? We're gonna do it the usual way of doing text or output files in Python. I'm gonna say with open the name of the file we wanna actually output. Let's call it data.json. We need to specify we are writing this file, so I'm gonna do that by saying W for write. If you do R, it's gonna be for reading. In this case, we are writing, so it's gonna be W. And you're gonna say as, and you can give it whatever name you want. Let's call it just file for now. And if you do JSON that dump means actually save this file. We're gonna save the dictionary, new data, into this file. But it's really helpful if you actually give it the indentation. So if you say indent, for example, 4, you will have that indentation between the keys. So let's save this and execute that. And now we have a new file called data.json. So if we inspect that one, you see how organized it looks. As before, when I was manually trying to create this dictionary by hand, this structure, now it looks with the proper structure we want. So we're gonna be using this a lot. So let's also read from that website. We're gonna do that by using the request library. So import request, and we need to fetch the URL from the same website. So we can copy this URL here, and we can specify a constant. So that's the URL. And now we can create a variable called response. And we're gonna call in that library request.get. We're getting something. You can also post, and we will do this when we are creating our API. But in this case, you wanna fetch an API. This is an endpoint in a website. We're trying to graph that one. So we can specify URL is that URL. This will connect to the website, to the server, fetch whatever is available for us as an API, and it will return lots of things. One of those things is that we can actually have, for example, let's call this D for dictionary, and it will be a method called JSON. This will be a long dictionary. Obviously, it's all the dictionary we have in the website is all of this. But let's just take a look. Maybe now we can actually print D. It's gonna be a long print. So it connects to the website, and now we have everything in the format we want. This is a regular Python dictionary, but we can also fetch the keys for this. So let's start modifying some of these JSON files. We have this one, data.json, that we created. Let's take a look how it's looking. It's a dictionary we did first. So let's create another Python script. Let's call this one JSON utils import JSON. So now let's manipulate that JSON file. And the first script we actually created that one, and here we're gonna manipulate it a little bit. So let's open it first. We're gonna do the usual with open the name of the file. It's called data.json. And this time we're gonna read the file. We're not gonna write to the file. That's file. And we can do JSON that load the file. We can store this in a variable actually. So let's call it D. And now if we print D, we will have that dictionary. So this is a usual Python dictionary. You see how it went back to the first dictionary I actually created, and how different it is from the structure we're using in production for JSON files. But we're reading, we have the data, and we can use that. So let's comment this one. And let's do some more utils. This time we're gonna update the JSON file. So let's do with open the same file, data.json. We're gonna read it as file as usual. And now we can do a variable again. This is very similar for what we just did. JSON.load, the file. But now we can actually say data.update. And we can pass in here a new data, for example. So let's create another dictionary here. Let's call this new data. And let's do one basic dictionary, just some keys and values. Like that, for example, very simple. And we're gonna update this one with the new data. So we can actually now save this one, and we can specify it as, we can update the same file, or we can create a new one. So if we wanna just update this one, let's try it like this. We're gonna execute this. You see how it's still the same original dictionary. So we actually need to trigger that save, and we do it this way. It's gonna be something very similar. With open the name of the file. This time we're gonna write to it as, call it differently, data file, for example. JSON.dump, remember that. Data file. This will be new data. Oh, sorry, it's this one, it's still data, that's fine. We're passing in the data file, and we can, as usual, set the ident. So if we now run that one, and we cat that, just to verify, now you can actually see it's not the same one as before. This is the original one, and we're just appending to the new one. So this is our new keys and values at the end. That way we can actually update the file, and we will use this a lot because it's just going to be basically one JSON file. As you can see, we're not creating a new one. It's always the same data.json. We're reading from it, we're grabbing all the information, we have new key value pairs, new information, and we just basically append into it. So that's how you do that.